GPT-2 model, the 124 million version of it. So when OpenAI released GPT-2, this was 2019, and they released it with this blog post. On top of that, they released this paper, and on top of that, they released this code on GitHub. So OpenAI/GPT-2. Now, when we talk about reproducing GPT-2, we have to be careful because in particular in this video, we're going to be reproducing the 124 million parameter model. So the thing to realize is that there's always a mini-series when these releases are made. So there are the GPT-2 mini-series made up of models at different sizes, and usually the biggest model is called the GPT-2. But basically the reason we do that is because you can put the model sizes on the x-axis of plots like this, and on the y-axis, you put a lot of downstream metrics that you're interested in, like translation, summarization, question answering, and so on. And you can chart out these scaling laws. Basically, as the model size increases, you're getting better and better at downstream metrics. And so in particular for GPT-2, if we scroll down in the paper, there are 4 models in the GPT-2 mini-series, starting at 124 million all the way up to 1,558 million. Now, the reason my numbers, the way I say them, disagree with this table is that this table is wrong. If you actually go to the GPT-2 GitHub repo, they sort of say that there was an error in how they added up the parameters, but basically this is the 124 million parameter model, etc. So the 124 million parameter had 12 layers in the transformer, and it had 768 channels in the transformer, 768 dimensions. And I'm going to be assuming some familiarity with what these terms mean because I covered all of this in my previous video, Let's Build GPT from scratch. So I covered that in the previous video in this playlist. Now, if we do everything correctly and everything works out well, by the end of this video, we're going to see something like this, where we're looking at the validation loss, which basically measures how good we are at predicting the next token in a sequence on some validation data that the model has not seen during training. And we see that we go from doing that task not very well, because we're initializing from scratch, all the way to doing that task quite well by the end of the training. And hopefully we're going to beat the GPT-2 124M model. Now, previously, when they were working on this is already 5 years ago, so this was probably a fairly complicated optimization at the time, and the GPUs and the compute was a lot smaller. Today, you can reproduce this model in roughly an hour, or probably less even, and it will cost you about $10 if you want to do this on the cloud compute, a sort of computer that you can all rent. And if you pay $10 for that computer, you wait about an hour or less, you can actually achieve a model that is as good as this model that OpenAI released. And one more thing to mention is, unlike many other models, OpenAI did release the weights for GPT-2, so those weights are all available in this repository. But the GPT-2 paper is not always as good with all of the details of training. So in addition to the GPT-2 paper, we're going to be referencing the GPT-3 paper, which is a lot more concrete in a lot of the hyperparameters and optimization settings and so on. And it's not a huge departure in the architecture from the GPT-2 version of the model. So we're going to be referencing both GPT-2 and GPT-3 as we try to reproduce GPT-2 124M. So let's go. So the first thing I would like to do is actually start at the end, or at the target. So in other words, let's load the GPT-2 124M model as it was released by OpenAI and maybe take it for a spin. Let's sample some tokens from it. Now, the issue with that is when you go to the code base of GPT-2 and you go into the source and you click in on the model.py, you'll realize that actually this is using TensorFlow. So the original GPT-2 code here was written in TensorFlow, which is, not, let's just say, not used as much anymore. So we'd like to use PyTorch because it's a lot friendlier, easier, and I just personally like it a lot more. The problem with that is the initial code is in TensorFlow. We'd like to use PyTorch. So instead, to get the target, we're going to use the Hugging Face transformers code, which I like a lot more. So when you go into the transformers, source, transformers, models, GPT-2, modeling, GPT-2.py, you will see that they have the GPT-2 implementation of that transformer here in this file. And it's like medium readable, but not fully readable. But what it does is it did all the work of converting all those weights from TensorFlow to PyTorch friendly, and so it's much easier to load and work with. So in particular, we can look at the GPT-2 model here, and we can load it using Hugging Face transformers. So swinging over, this is what that looks like. from transformers, import the GPT-2 LM head model, and then from pre-trained GPT-2. Now, one awkward thing about this is that when you do GPT-2 as the model that we're loading, this actually is the 124 million parameter model. If you want the GPT-2, the 1.5 billion, then you actually want to do -XL. So this is the 124M, our target. Now what we're doing is when we actually get this, we're initializing the PyTorch NN module as defined here in this class. From it, I want to get just the state dict, which is just the raw tensors. So we just have the tensors of that file. And by the way, here, this is a Jupyter Notebook, but this is Jupyter Notebook running inside VS Code. So I like to work with it all in a single sort of interface. So I like to use VS Code. So this is the Jupyter Notebook extension inside VS Code. So when we get the state dict, this is just a dict. So we can print the key and the value, which is the tensor, and let's just look at the shapes. So these are sort of the different parameters inside the GPT-2 model and their shape. So the W weight for token embedding is of size 50,257 by 768. Where this is coming from is that we have 50,257 tokens in the GPT-2 vocabulary. And the tokens, by the way, these are exactly the tokens that we've spoken about in the previous video on my tokenization series. So the previous video is just before this. I go into a ton of detail on tokenization. GPT-2 tokenizer happens to have this many tokens. For each token, we have a 768 dimensional embedding that is the distributed representation that stands in for that token. So each token is a little string piece, and then these 768 numbers are the vector that represents that token. And so this is just our lookup table for tokens. And then here we have the lookup table for the positions. So because GPT-2 has a maximum sequence length of 1024, we have up to 1024 positions that each token can be attending to in the past. And every one of those positions in GPT-2 has a fixed vector of 768 that is learned by optimization. And so this is the position embedding and the token embedding. And then everything here is just the other weights and biases and everything else of this transformer. So when you just take, for example, the positional embeddings and flatten it out and take just the 20 elements, you can see that these are just the parameters. These are weights, floats, just we can take and we can plot them. So these are the position embeddings. They're weights, example, the positional embeddings. and flatten it out and take just the 20 elements, you can see that these are just the parameters. These are weights, floats, just we can take and we can plot them. So these are the position embeddings. And we get something like this, and you can see that this has structure. And it has structure because what we have here really is every row in this visualization is a different position, a fixed absolute position in the range from 0 to 1024. And each row here is the representation of that position. And so it has structure because these positional embeddings end up learning these sinusoids and cosines that sort of like represent each of these positions. And each row here stands in for that position and is processed by the transformer to recover all the relative positions and sort of realize which token is where and attend to them depending on their position, not just their content. So when we actually just look into an individual column inside these, and I just grabbed 3 random columns, you'll see that, for example, here we are focusing on every single channel, and we're looking at what that channel is doing as a function of position from 0 to 1023, really. And we can see that some of these channels basically like respond more or less to different parts of the position spectrum. So this green channel really likes to fire for everything after 200 up to 800, but not less, but a lot less, and has a sharp drop off here near 0. So who knows what these embeddings are doing and why they are the way they are. You can tell, for example, that because they're a bit more jagged and they're kind of noisy, you can tell that this model was not fully trained. And the more trained this model was, the more you would expect to smooth this out. And so this is telling you that this is a little bit of an under-trained model. But in principle, actually, these curves don't even have to be smooth. This should just be totally random noise. And in fact, in the beginning of the optimization, it is complete random noise because this position embedding table is initialized completely at random. So in the beginning, you have jaggedness, and the fact that you end up with something smooth is already kind of impressive, that just falls out of the optimization, because in principle, you shouldn't even be able to get any single graph out of this that makes sense. But we actually get something that looks a little bit noisy, but for the most part looks sinusoidal-like. In the original transformer paper, the attention is all you need paper, the positional embeddings are actually initialized and fixed, if I remember correctly, to sinusoids and cosines of different frequencies. And that's the positional encoding, and it's fixed. But in GPT-2, these are just parameters, and they're trained from scratch, just like any other parameter. And that seems to work about as well. And so what they do is they kind of like recover these sinusoidal-like features during the optimization. We can also look at any of the other matrices here. So here I took the first layer of the transformer and looking at like one of its weights and just the first block of 300 by 300, and you see some structure, but like, again, like who knows what any of this is. If you're into mechanistic interpretability, you might get a real kick out of trying to figure out like what is going on, what is this structure, and what does this all mean, but we're not going to be doing that in this video. But we definitely see that there's some interesting structure, and that's kind of cool. What we're mostly interested in is we've loaded the weights of this model that was released by OpenAI, and now using the Hugging Face transformers, we can not just get all the raw weights, but we can also get the what they call pipeline and sample from it. So this is the prefix, hello, I'm a language model, comma, and then we're sampling 30 tokens, and we're getting 5 sequences, and I ran this, and this is what it produced. Hello, I'm a language model, But what I'm really doing is making a human readable document. There are other languages, but those are ... So you can read through these if you like, but basically these are 5 different completions of the same prefix from this GPT-2 124M. Now, if I go here, I took this example from here. And sadly, even though we are fixing the seed, we are getting different generations from the snippet than what they got. So presumably the code changed. But what we see though at this stage that's important is that we are getting coherent text. So we've loaded the model successfully. We can look at all its parameters, and the keys tell us where in the model these come from. And we want to actually write our own GPT-2 class so that we have full understanding of what's happening there. We don't want to be working with something like the modeling GPT-2.py because it's just too complicated. We want to write this from scratch ourselves. So we're going to be implementing the GPT model here in parallel. And as our first task, let's load the GPT-2 124M into the class that we're going to develop here from scratch. That's going to give us confidence that we can load the OpenAI model, and therefore there's a setting of weights that exactly is the 124 model. But then of course what we're going to do is we're going to initialize the model from scratch instead and try to train it ourselves on a bunch of documents that we're going to get. And we're going to try to surpass that model. So we're going to get different weights and everything's going to look different, hopefully better even. But we're going to have a lot of confidence that because we can load the OpenAI model, we are in the same model family and model class, and we just have to rediscover a good setting of the weights, but from scratch. So let's now write the GPT-2 model, and let's load the weights and make sure that we can also generate text that looks coherent. Okay, so let's now swing over to the attention is all you need paper that started everything, and let's scroll over to the model architecture, the original transformer. Now, remember that GPT-2 is slightly modified from the original transformer. In particular, we do not have the encoder. GPT-2 is a decoder-only transformer, as we call it. So this entire encoder here is missing. And in addition to that, this cross-attention here that was using that encoder is also missing. So we delete this entire part. Everything else stays almost the same, but there are some differences that we're going to sort of look at here. So there are 2 main differences. When we go to the GPT-2 paper under 2.3.model, we notice that first, there's a reshuffling of the layer norms, so they change place. And second, an additional layer normalization was added here to the final self-attention block. So basically, all the layer norms here, instead of being after the MLP or after the attention, they swing before it, and an additional layer norm gets added here right before the final classifier. So now let's implement some of the first sort of skeleton NN modules here in our GPT NN module. And in particular, we're going to try to match up this schema here that is used by Hugging Face transformers, because that will make it much easier to load these weights from this state dict. So we want something that reflects this schema here. So here's what I came up with. Basically, we see that the main container here that has all the modules is called transformer. So I'm reflecting that with an NN module dict. And this is basically a module that allows you to index into the submodules using keys, just like a dictionary, strings. Within it, we have the weights of the token embeddings, WTE, and that's an NN embedding, and the weights of the position embeddings, which is also just an NN embedding. And if you remember, NN embedding is really just a fancy little wrapper module around just a single array of numbers, a single block of numbers just like this. It's a single tensor. And NN embedding is a glorified wrapper around a tensor that allows you to access its elements by indexing into the rows. Now, in addition to that, we see here that we have a .h, and then this is indexed using numbers instead of indexed using strings. So there's a .h, .0, 1, 2, etc., all the way up till .h.11. And that's because there are 12 layers here in this transformer. So to reflect that, I'm creating also an H, I think that probably stands for hidden. And instead of a module dict, this is a module list. So we can index it using integers, exactly as we see here, .0, .1, 2, etc. And the module list has n layer blocks, and the blocks are yet to be defined in a module in a bit. In addition to that, following the GPT-2 paper, we need an additional final layer norm that we're going to put in there. And then we have the final classifier, the language model head, which projects from 768, the number of embedding dimensions in this GPT, all the way to the vocab size, which is 50,257, and GPT-2 uses no bias for this final sort of projection. So this is the skeleton, and you can see that it reflects this. So the WTE is the token embeddings. Here it's called output embedding, but it's really the token embeddings. The PE is the positional encodings. Those two pieces of information, as we saw previously, are going to add and then go into the transformer. The .h is all the blocks in gray, and the LNF is this new layer that gets added here by the GPT-2 model. And LM head is this linear part here. So that's the skeleton of the GPT-2. We now have to implement the block. Okay, so let's now recurse to the block itself. So we want to define the block. So I'll start putting them here. So the block, I like to write out like this. These are some of the initializations, and then this is the actual forward pass of what this block computes. And notice here that there's a change from the transformer again that is mentioned in the GPT-2 paper. So here, the layer normalizations are after the application of attention or feed forward. In addition to that, note that the normalizations are inside the residual stream. You see how feed forward is applied and then this arrow goes through and through the normalization? So that means that your residual pathway has normalizations inside them. And this is not very good or desirable. You actually prefer to have a single clean residual stream all the way from supervision, all the way down to the inputs, the tokens. And this is very desirable and nice because the gradients that flow from the top, if you remember, for